This will be a horrible recording with my voice, but oh well, it's better than nothing, maybe. Okay, so on page 19, looking at the problem down below, it says an 80 kilogram block and a 40 kilogram block are connected with a rope of negligible mass. And y'all, that's the moral of the story. Our ropes, the Twizzler that we did last time, they don't have mass unless told otherwise. And hint, hint, there is one of the NIMSY free response. They don't put boxes on their ropes. They just let the rope go over a pulley. So, you know, different sides of the pulley will have different masses of the rope. And so overall, though, most times the rope is negligible. The 80 kilogram block is placed on a horizontal surface. And so this one is our 80 kilogram. Well, the 40 kilogram block is placed on a 40-degree incline. And so we've got the 40 kilograms, not to be confused with our theta of 40 degrees. The objects are released from rest and allowed to slide. You may assume all surfaces are frictionless. And that's where you do a little happy dance. Yay, no friction. And to kind of, your lab isn't exactly the same way. However, in today's lab, we are assuming no friction. That's real life. Is there really friction? Yeah, so we're not going to get the best results, but it should be close enough to feel good about the physics, okay? But yay, no friction, no mu Fn. What is the acceleration of the blocks? And what is the tension in the rope connecting them? And then part C, what if we swap the blocks on the horizontal surface and the incline? Would the tension increase, decrease, or stay the same? So let's start out. Step one to any force problem is what? A diagram. And so starting with, maybe I put 80 over here in the left margin. And so what forces are acting on the 80 kilogram block? Gravity. And 80 kilogram to 40 kilogram, 80 is going to be twice the mass, twice the weight. So, you know, you don't have to go crazy. But FG 80 there. What other forces? Normal is going to go what direction on the 80 kilogram? Straight up. How big do I draw it? Equal to the weight of the 80, right? Because it's on a tabletop and there's no other vertical forces. So these two are equal and opposite. Newton's first law. When you balance on one object, it's first law. Okay. What other forces are acting on the 80? Tension is going to pull on it. Bless you. The string pulls parallel to the string, so to the right. Now we don't know how much yet, right? So I don't want to equal to those others. So maybe something like this. And no friction, yay! So that's it on the 80 kilogram. What forces are acting on the 40? We got gravity, it's half the mass, half the weight, okay? Just not too small, so I'm gonna maybe go right there. FG 40. What other forces are acting on the 40? Normal is going to be tilted, right? And so if your ramp tilts the x-axis 40 degrees, the normal force goes from old y straight up and tilts 40 degrees to the right. Tilt your head to the right. And it's going to be smaller than FG 40. And if you forgot why, we'll hit it in just a second. What else? Right, the rope is pulling up the ramp on this block. And so how big do I draw it? Not necessarily bigger than both of these. equal to the tension on the other. And so when you have multiple objects, I'm going to use 2 tick marks on this one. When you have multiple objects either directly pushing on each other, a normal force, or connected through a string, they're still pulling on each other. So those are equal and opposite on 2 separate objects. Tell me which of Newton's laws this is. Newton's third law. And so just make a note here so you can tell the difference. The normal force and gravitational force on the 80, just note to self, those are equal because of Newton's first law. So just saying equal and opposite, slow down, slow down. Any other forces on the 40 kilogram on the ramp? No more actual forces since it's frictionless, right? However, we can do a little something. You don't do this on the AP exam, chicken scratch it on the side. We're going to break that FG40 into components. So here's the last time you're going to see me do this. Make sure you practice this before the exam, right? You got to be able to duplicate this. And so I start with, well, Fn is on the new y-axis. FG perpendicular is going to be balancing that normal force. And so Fn is going to equal FG perpendicular 99% of the time. It's been 100% of the time in our practice, by the way. Always give AP the, the curveball, 1%. And then this is the new y-axis, new perpendicular. So our angle is at the separation. It's at the top there. So whatever the x-axis shifts, so does your y-axis. And then you complete the triangle by drawing FG parallel to the surface. And your final check is what? To make sure you've drawn the triangle correctly. FG should be the hypotenuse. If it's not, erase and readjust. And so how do you know the hypotenuse? Well, your components should form a 90-degree angle with each other, meaning FG, the actual weight, is your hypotenuse. Good deal on that? Okay. I've already forgot what we're doing. Oh, acceleration. Okay, so force diagrams, step 1. Step 2, FNet statements. And so let's see. Trying to fit them both on here. And so FNet statements, so this is part leading up to A. And so we want our FNet. And so FNet for the 80 in the direction of motion, and I guess we need to identify, so step 1.5, what's going to be our forward direction? It's all frictionless. Who's going to pull who? Okay, so the 80 is going to go to the left, forward. No, wait, to the right. Sorry, in my head, I thought you were, this is to the right. So if it's all frictionless, the one on the ramp is going to drive the system, right? And so our 40 will go down the ramp, and you're like, but it's less mass. You're going to see that today, that a very small mass can accelerate a big system, okay? You'll see it. And so the 40 is going to go down the ramp, forward, and the 80 is going to go to the right, forward. If you look at the 80, there's only a rightward force pulling on it. So if it's released from rest, that's all it can do.
You may have already caught this, but I was going to.
Okay, so 80 goes to the right, forward, 40 goes down the ramp, forward. Everybody good? Okay, and so now the 80 kilogram FNet statement in the direction of motion is just going to be a positive tension. What about for the 40? Think about the forward direction. Who's pulling it down the ramp? FG parallel. And so it's FG parallel. Who's trying to pull it up the ramp? FT. If there was friction, we would have minus frictional force, right? But it's frictionless on this one. Thank you. One less step. All right. To get acceleration of each block is the same as the acceleration of the system. And so we can add these two equations together and get F net of the system, or you can say F net 80 plus F net 40. And notice what happens to the tension. Goes Newton's third law, action-reaction pairs should do what from a system approach? Cancel. Not that they zero. Careful, they don't zero out. You have tension, right? They just are equal and opposite. And so the only thing driving this, and I'm just adding a 40 there so we get the right mass. The only thing driving the system is that FG parallel for the smaller block. Now, let's break it down. Everybody says F net equals MA, which mass? System. Equals FG parallel. Let's go back to our triangle. Or maybe by this point, you have it memorized. What's our equation for FG parallel? MG or FG sine theta. Just make sure you get the right mass, okay? And so it's going to be M of the 40 block times G, and then sine theta. And then to solve for acceleration, I'm going to take that M40 G sine theta and divide by system mass, but in this step, it's just the sum of the masses. So it's the M40 plus the M80. Now I'm not really plugging numbers in just yet, okay? Notice I got M40 top and bottom. Does it cancel? No, it doesn't cancel, okay? Nothing cancels here. And so notice it's just 40 times 10. And then our angle is also 40 degrees. I don't want you thinking I'm plugging in the mass twice. And then the sum of our masses. And so work it out. .14. Okay. Now I kind of want to add another question just to be, kind of full picture. C says, what if we swapped the masses? What happens to the tension? But what if we do, A.5, question A.5, what if we swap the masses? How would that affect the acceleration? What changes in the variable? The angle's the same, the planet gravity is the same, the system mass is the same, but look, the one on the ramp is going to be bigger. So what's going to happen to your acceleration if we swap the masses? It would increase. Your denominator stays the same, but the driving force increases, right? And so you would have a greater acceleration. So it would be a direct relationship there. Okay. Everybody good? Then it says, find the tension. And so the tension equation is not on the formula chart. No, I can't tell you the equation to use on test day. You have to write the equation. Or maybe you already did. Didn't we already write an equation that involves tension? We have two. And if Newton's third law is correct, I can use either one. So what do y'all want to use, the 80 or the 40 equation? The 80, there's only one piece to it, right? And so for part B, to find the tension, I can just use F net 80 And it's already isolated for tension. F net equals MA, but which mass? I got to be consistent. Okay, subscripts are there to help you. So if we use 80 times the acceleration we just found, what do we get? Yeah. So 171 newtons. Good deal. All right, well then part C, swap the masses again, right? And this really is helpful when it's frictionless. Okay, it gets more complicated when there's friction because you have friction on a different normal force. But if you swap the masses, what happens to the tension? Right, and so for part C, when we swap the masses, if we're consistent and say, well, tension equals M40A, right? Mass decreases, but be careful. Previously, what did we say about acceleration? It would increase. Well, does a decrease, increase net out to be the same? I wouldn't, there's angles involved. Let's actually go through it, okay? And so the acceleration, here's a trick. So to save you a little bit of math, we know an equation for the acceleration. Can I plug that in here? I just have to make sure I switch the mass. And so your tension with them swapped would be M40, but then be careful, M40 in my previous acceleration is now going to be M80, right? And so it would be M80 times G sine theta over M40 plus M80. And so you can plug numbers in, or notice, isn't it basically the product of the masses divided by the sum of the masses, all times G sine theta? Do a little algebra with the variables. So whether you swap the masses or not on this one, you get the product, that would be the same, and the sum, that would be the same. Yes? Or work it out and let's see. So 40 times 80 times 10 sine, same angle, over 40 plus 80. And I get 171. Same thing. I added the 0.4. I probably should have just not. I got the same thing earlier. So you actually get the same tension. Whoa, Miss Earhart, does this mean any problem that switches the masses will get the same tension? No, I would test that theory before you do it, right? Go back to other problems, switch the masses and see. But the answer is no. One of the reasons it works out this way, it was frictionless. Not every problem is frictionless, right? So if you added friction in the mix, then you still have the same coefficient. It's still mg cosine theta, but that m is going to be different. And so you'd have a subtraction or something on the top with a different mass. What makes this one nice, since it's frictionless, you get the same. And so note, it's the same tension, but warning, frictionless is the main reason why, okay? But it kind of goes back to that same thing. They're pulling on each other. Together, they determine the tension, right? Together. So it's pretty neat. Questions on that one? Hopefully that wasn't too bad. Maybe when you first looked at it, you're like, oh no, a ramp and a tabletop. We've never done one like that. But hopefully it felt very familiar based on the ones we did do, okay? Always force diagram, always F net. If that's not your habit by Tuesday, by May, then something's wrong. You're not practiced enough, okay? So just another reminder, if you have not been doing independent practice, I highly recommend 2 to 3 hours of independent practice, meaning you look at a blank page, maybe go back, if you haven't done 17, it's kind of got a mixture of problems there, okay? Hopefully they feel familiar. Okay, this is a good, not that this is the only practice I think you should do, but if you're like, I only have time for one page, make 17, okay? Because you have a ramp, you have a friction with coefficient, you've got some angles there, right? Now there's not a pulley, so I would ask that you at least try some kind of pulley problem on your own, but do some variety, 2 to 3 hours before the exam, okay? Forces is so variance. You got to be ready. Good deal? All right, let's transition to lab.